Because I spent yesterday inventing Special Quiz 2.
You didn't go trick-or-treating?
Pardon?
I said you didn't go trick-or-treating?
Trick-or-treating?
Why not?
Oh, I did. That's my trick-or-treat for you folks. See, I'm the witch goblin that stands at the door. You're the kid that comes and knocks on the door and says, "Give me stuff or I'll be rough." That's what I saw in the funny papers today, rather than trick or treat. I thought that was kind of cute. Little kid, "Give me stuff or I'll be rough." This will be all on stuff you've done. So I'm giving you 2 weeks, more or less. Plenty of time. It's not quite done. I know what I want to ask, but I haven't figured out yet how I want to ask it regarding the last question. It'll be up this afternoon. Now then, back to fundamental aspects of thermodynamics, which I remind you again we've done so far all along, nothing else. All we've done so far is thermodynamics. Most of what you did in 2045 is thermodynamics, given that it's quite amenable to study in first-year chemistry. And most important, back to our experiment. Imagine we have a piston cylinder gadget at these conditions in which we have contained 1.00 moles of N2O4 gas. Next to it, another piston cylinder gadget. But in this piston cylinder gadget, we have 2.00 moles of NO2 gas at the same conditions. If we treat these gases as capable of exhibiting ideal behavior, which means their behavior is describable by P equals nRT, a fair statement for these gases. Approximate volumes will be 25 liters. In the first piston cylinder gadget, where we got 1 mole, 2 moles, 50 liters. Need big gadgets if we were going to do this experiment. But it's the experiment we can't do, but can discuss, which we do right now. And last time we showed you a flask, actually a couple of 3 flasks that contain NO2 gas as well as N2O4 gas. And we showed you what happened inside this flask if we warm or cool. Warming, supplying heat, provoking an endo transformation, provoking bond breaking, provoking the decomposition of colorless N2O4 into brown NO2. Cool, energy extracting, supporting exo reactions, provoking bond formation. Hey, you know this. You want to increase the strength of hydrogen bonding among and between water molecules, given that hydrogen bonding is the strongest type of intermolecular attraction force in that sample of matter? What do you do with the water? Heat it up or cool it off? Put it in a pot on a stove and boil it? Or put it in your refrigerator freezer? You know damn well the refrigerator freezer is where you get the water molecules to get together very strongly and form this stuff called ice. Said, if you think water molecules in the vapor state are bound to each other more strongly than water molecules in the solid state, boil your water and over the water pot do this. I mean away from the concentrated heat of the evaporating water. See how much resistance you feel. Then take your ice cubes, throw them up in the air and go like this. See if you feel any greater resistance. You know the answer to this. I told you to write Lewis pictures for these things. I won't ask for a show of hands to find out how many did this. But first course of action in writing a Lewis picture is count dots. For this molecule, you get 17 dots. It's an odd electron molecule. That guarantees it has to be a radical. Remember what a radical is? Ask you to learn that definition by way of the work that you did in the Tinker Toys experiment. Assignment 645 laboratory. Yeah, I know. You may be thinking, you mean this bastard thinks we remember what we did in 45 laboratory? I don't know that I think you remember it, but I know damn well I sure as hell hope you do.
Species that contains unpaired electrons.
One or more unpaired electrons in the valence environment, that's a radical. Because if you got an odd number of electrons, all the valence electrons can't be paired. So you're looking at a species which has got to be paramagnetic. That language you learn in 2045. Now in writing a Lewis picture for this paramagnetic molecule, strikes me the only reasonable conclusions you could reach would be this Lewis picture for which each component atom has zero formal charge. Or this Lewis picture where the central nitrogen atom has a formal charge of +1 and this oxygen atom, the so-called singly bonded oxygen atom, has a formal charge of -1. Do you think for this molecule there is in actuality an NO double bond and an NO single bond? Do you think for this molecule, if you could see it, you'd see one O atom closer to the nitrogen atom than the other? The doubly bonded oxygen closer to the nitrogen atom, would you see that? What would you see? What would you see? In terms of bond lengths, they'd be identical, wouldn't they? And if you did bond strength measurements, you'd find out that the NO bonds in this molecule were each shorter and stronger than an actual NO single bond, but longer and weaker than an actual NO double bond. Resonance, of course, is the property to which we are referring for the NO bonds in this molecule. Bond orders 3/2. The 3 bonding electron pairs total, parceled over 2 bond sites. 3 divided by 2 gives us our bond order of 1.5 or 3/2. But which Lewis picture do you prefer? In terms of bond order, the Lewis pictures are identical. But in terms of valence electron environment, this zero formal charge distribution species or this ± formal charge distribution species. Tell me, is this kind of formal charge separation a violation of Coulomb's law, or does it keep with Coulomb's law? Does it have opposite sign formal charge on adjacent bound atoms? Which means in a molecule, that's as close as you could get these opposite charges to each other. So does Coulomb like the opposite charge close to each other or far away? What does Coulomb like? Opposite charges close to each other because they stick to each other, or far away from each other because opposite charges repel each other. Is that true? Do opposite charges repel each other, Coulomb? Hell no, they attract each other. So that's not a violation of Coulomb's law. But it does show that in this Lewis picture, each oxygen atom is in an octet environment, whereas in this Lewis picture, the nitrogen atom is also in an octet environment along with this oxygen atom, but this oxygen atom is deficient relative to octet. So you need to consider one other property of atoms to decide which of these Lewis strictures is the best representation of the valence structure of NO2. What is this other property to which I refer? I think I heard it very faintly.
Electronegativity.
Yup! Electronegativity, you're damn right. Which atom is of greater electronegativity? Did you learn in 2045 that it's a lot of fun to think about electronegativity? A lot of fun. Fluorine, oxygen, nitrogen. A lot of fun. Fluorine's number 1, oxygen's number 2, nitrogen's number 3. Now chlorine and nitrogen have pretty near the same electronegativities. But I use the device FON because there's a hell of a lot more important nitrogen-containing molecules than are those which contain chlorine. You believe amino acids are important? You learned something about amino acids on Special Quiz 1? How about that? I ask you this stuff because this stuff's important. Let's learn chemistry about important stuff. So which of these Lewis structures actually is the better representation of the true valence structure of NO2? Is it this one? Let's call this one A, or this one? Let's call this one B. Which one? How many vote for A? How many vote for B? Okay. And now we get to the proof of the pudding. Because this experiment involves this equilibrium reaction, or relates to this equilibrium reaction. I can write this reaction in either direction. It doesn't make any difference, except that if I write it in the opposite direction to the way I've now written it, then the equilibrium constant will be the partial pressure of this squared in the numerator and the partial pressure of this in the denominator. Whereas if I write it this way, it's the partial pressure of this in the numerator and the partial pressure of this squared in the denominator. So the value for the equilibrium constant this way, at the same temperature, will invert to give me the value for the equilibrium constant in this direction, if I consider the same conditions applying. This way it's strictly bond forming. We talked about this the other day. This way it's strictly bond breaking. This way in exo, this way endo. Did you write a Lewis picture for N2O4? Statement. Do you realize that just from this reaction equation alone, as NO2 molecules get together to make N2O4 molecules, which is a bond-forming process, what kind of bond is it possible to form just from this reaction equation alone? Could we be making another NO bond? Would that be possible? Could we be making an OO bond? Would that be possible? Could we be making an NN bond? Would that be possible? All these are possible just from that equation alone. Because those formulas as they are written don't show you anything about structure, but these do. So, if our Lewis structure analysis is correct, and B is the correct picture for the valence electron environment of NO2, what bond do you think we make when these molecules get together to become this molecule? What bond do you think we make? NN, OO, or NO? NN, period. And that's what we find. When you examine the structure of this thing, you find out that it contains an NN bond. How about that? It tells us. The unpaired electron on this nitrogen is ready to partner up with the unpaired electron on the other nitrogen in the other NO2 molecule, and wham, there comes the formation of the NN bond. All of this is concludable from this analysis. Structure, the most important property of a chemical species, period. That's why this stuff is so important, to write these pictures. All right, back to our experiment. We're imagining to run this experiment, and then after each piston cylinder gadget stands for a long time, we're going to pry them open to investigate the contents of each piston cylinder. What shall we find? Now then, take note, for this reaction as written, delta G0R equals minus 4.7 kilojoules. What does that tell you? At 25 centigrade, 1 atmosphere, which is more thermodynamically stable? 1 mole of N2O4 gas or 2 moles of NO2 gas? What does that data point tell you? Which is the more stable form of substance? 1 mole of N2O4 gas or 2 moles of NO2 gas? 1 mole of N2O4 gas. So back to our experiment. We're prying open the piston cylinder gadgets. What shall we find? Will we find in this piston cylinder gadget that the N2O4 originally placed within is stayed and nothing has happened? And that in this piston cylinder gadget, all the NO2 molecules have become N2O4. Is that what we're going to find? Because we're going to let this stand for an infinite amount of time. We're not going to have any kinetic barrier to the outcome of this thermodynamic experiment. Is that what we'll find? If that's true, then the volume of this piston cylinder will stay the same as time passes, whereas the volume of this piston cylinder will reduce to become the volume of this piston cylinder. Now let me tell you what we'll observe from a volume standpoint. As time passes, the volume in this piston cylinder increases. And as time passes, the volume in this piston cylinder decreases until the volumes become equal. So that part of our speculation is correct. The resultant volumes are equal. But the volume in this piston cylinder did not stay the same. It increased. What's going on here? Tell me. Which is the more stable form of matter at 1 atmosphere 298 K? 2 moles of NO2 gas, 1 mole N2O4 gas, or an equilibrium mixture of these gases? Which is the most stable? Equilibrium mix, isn't it? Because any reaction system, isn't this true, Le Chatelier? Huh? Any reaction system from a thermodynamic standpoint will react so as to get to, if possible, what? Equilibrium. You betcha. So when we open these piston cylinder gadgets, besides finding the same volume for each, we find exactly the same composition. Let's examine that from this G-state graph. G, again, is a property of material we cannot measure, but we can discuss it. We've recognized that since delta G0 R for this reaction, written as it is written, is minus 4.7 kilojoules, that 2 moles of NO2 gas is not as thermodynamically stable as 1 mole of N2O4 gas. So on my G-state graph, I'll purposely put the mole of N2O4 gas over here, and the 2 moles of NO2 gas higher. It has a higher G-state. Less stable. Because the lower your content of energy, the more stable you are. So this is the more stable stuff. And if I take the difference in G state level for the 1 mole of N2O4 gas and 2 moles of NO2 gas, which is this, I get delta G0R for this reaction, if I make the measurements under standard state conditions. Minus 4.7 if the 2 moles of NO2 gas react entirely and become 1 mole of N2O4 gas. But plus 4.7 kilojoules if I input energy and make the 1 mole of N2O4 gas decompose entirely so as to become 2 moles of NO2 gas. But what have I found in each piston cylinder gadget? Neither pure substance. I found the equilibrium mix, the result of which is this system is screaming at us. We are by far, or I am by far, the most stable in the equilibrium state. So if I start with the 1 mole of N2O4 gas, is the change in G going to go this way? No, it's not. It's going to come down here to the equilibrium G state. Because the equilibrium G state, right here, G EQ, has got to be the most stable G state, not only for this, but for any system from a thermodynamic standpoint. The equilibrium G state. Because we recognize matter's not what we start with, we wind up with the equilibrium. So if we start with a mole of N2O4, it doesn't go this way from a change in G standpoint, it goes here. And if I start with the 2 moles of NO2, it doesn't go straight this way, it goes here. And notice that the change in G from 2 moles of NO2 down here to the equilibrium G state is bigger from a magnitude standpoint than the change in standard free energy, isn't it? And I also notice, if I start with the 1 mole of N2O4, hey, any change toward NO2 alone is an increase in G state, but that's not what happens. This comes down here and becomes a lower G state by getting to the thermodynamic condition. And only after it gets here does the G state begin to rise after having started with 1 mole of N2O4. This also reacts favorably because the change in G is negative, spontaneous. Just like here. It would be, of course, negative if it stops here, but that's not where it stops. It stops here and liberates more free energy than it would if it had stopped here instead. Interesting, isn't it? All screaming at us. Doesn't make any difference what mixture you start for a reaction system. If at all possible, it always will get to the equilibrium condition, because that's the most stable thermodynamic state in which the system can exist. Okay? Now then, notice, just kind of for fun, that this transformation shows us that the 2 thermodynamic properties of which G itself is composed, enthalpy and entropy, are real. Because if only enthalpy existed, and the only possible forms of matter were N2O4 or decomposed N2O4 is NO2. If those were the only possible forms of nitrogen-oxygen matter, from an H standpoint, we would only have N2O4 and never have NO2. Because its enthalpy is lower. Bonds are stronger in N2O4. Aha! But if only S existed, S says I can't stand bonds, I don't want any bonds. So only NO2 would exist, and never N2O4. So just for fun, if the cosmophysicists are right, and we all got started from this great Big Bang, it strikes me that if that's true, way back then, from a material standpoint, enthalpy was ruling the roost. Enthalpy loves bonds, hates motion, hates any increase in temperature. Wants absolute zero and nothing but strong bonds. No motion. Just a blob of motionless material at 0 Kelvin. But entropy says, I can't stand you. I want particle freedom. I want you to be able to move. I can't stand bonds, and I like high temperatures. Pow! And here comes free energy into the picture. The blend of enthalpy and entropy. And here we have it today. And which of these parts is continuing to increase? Do you know that the cosmos scientists have evidence to believe that the universe is perpetually doing what? Increasing, isn't it? Here comes entropy, saying, ha ha ha. More space, more freedom of motion. And on it goes. Until perhaps we could imagine coming to the so-called heat death of the universe, where entropy for all stuff in the universe has become one and the same. And then there can be no more change in entropy. When will that happen? At a time equal to something called infinity. So I wouldn't worry about it too much. Let's get back to our stuff. Now, to proceed with establishing, from a quantitative standpoint, a straightforward way by which we can wrestle with thermodynamic analysis of systems. Question 2121. Does calcium carbonate dissolve spontaneously in deionized water under normal lab conditions? Here's some calcium carbonate. And before you answer this question, let me tell you, by way of experiment, you've already answered this question. You answered in 2045 lab, and you answered it again in 2046 lab. In 2045 lab, you answered it in assignment 4. In 2046 lab, you answered it in assignment 3. Isn't it interesting how this lab work relates directly to what we're doing in here? So let's go back to 2045 lab. We have to be archaeologists now, because I know for many of you that's considered ancient history. In 2045 lab, how many of you remember mixing together sodium carbonate solution with calcium chloride solution? Remember that? And as soon as you made that mix, wham, out fell calcium carbonate. Out fell calcium carbonate. You were asked to filter to separate the calcium carbonate precipitate from the solution part of the mixture, and then wash the calcium carbonate with some deionized water, taking advantage of the fact that calcium carbonate isn't particularly soluble in water. I'm sure you've all recognized that if people were fairly soluble in water, you'd take one shower. And away you'd go. You'd go swimming once. That's it. And the ocean would be 1 molar U or something like that. Okay? And after you got this calcium carbonate clean, you were asked to take a spatula sample of it and stir it up into about 50 milliliters of deionized water, at which point in 45L assignment 4 you had already observed the conductivity of deionized water with these handheld conductivity gadgets, which are pretty reliable gadgets, but which are not sufficiently sensitive to pick up the very tiny total moles of ions concentration that you have in water. What's total ion concentration in water? Total ion concentration, water, NLC. Total ion concentration, water. Normal lab conditions, what is it? I'm listening. Do we have to go back to assignment chapter 18? Hydronium ion, 1 times 10 to minus 7. Hydroxide ion, 1 times 10 to minus 7. Those are molar concentrations. So what's the total ion concentration? 2 times 10 to minus 7. How about that? That's not a very high ion concentration. Your handheld conductivity gadgets were not sufficiently sensitive to pick that up. Now then, let's get back to the calcium carbonate experiment. The deionized water itself shows no measurable conductivity with your handheld gadgets. You now stirred the calcium carbonate into the deionized water to the extent of preparing saturated calcium carbonate solution. All you got to do is stir for a while and see that some calcium carbonate remains in the system undissolved. So you know you've maximized the amount of calcium carbonate which has dissolved. And then you reobserve conductivity. At that point, did you or did you not get an on-scale observable conductivity reading? What did you get? Nobody remembers? Everybody now flunks 45L, and you can go back and retake this course, because I have complete control over the grades for this. So I'm going to look up your name, every one of you. Everybody gets an F. And you go back to 45L. and do this course from the standpoint of learning what the hell it asks you to learn. How about that for an attitude? If I could get this dumb administration to realize this team stuff is nonsense, we could get someplace with this course. It's a good course, but it's so diluted that it winds up meaning hardly anything. Yes, you got an on-scale conductivity rating. It wasn't much. The numbers were about 10 or 15, so what? But the very fact that you got an on-scale conductivity rating allows you to answer this question. Does calcium carbonate dissolve spontaneously in water, in deionized water under normal lab conditions? Yes or no? Did some of the calcium carbonate dissolve to give you this on-scale conductivity rating? Well then, damn it, it dissolved spontaneously. All you did was mix up the calcium carbonate with the water. The point of this conversation is to get you to realize the big difference that exists between these thermodynamic property functions for reactions. Because the calcium carbonate dissolves spontaneously from this standpoint. Now what about this standpoint? What does this mean? What does it mean? Standard conditions. What are standard conditions for this transformation? If you are told to go to the laboratory and make this system under standard state conditions, you got to have some of this, because this is a pure solid, so by definition it's in the standard state. Some. Okay? There, you got some. Okay? Oh! He was dozing. How about that? Okay, now you got some calcium carbonate. Be sure you crumble it up. I want you to share it with everybody. Okay? And you have to have this in solution at what concentration? 1 molar. And this in solution at what concentration? 1 molar. Do you think you could prepare this system and have it exist? Do you think this at a molarity of 1 and this at a molarity of 1 will live with each other in the same system? Hell no. What will they do? What will they do? They'll react to do what? Make calcium carbonate until I get that. Because that's the molarity, the solubility of calcium carbonate in water at normal lab conditions. So, difference. Just like this. Here's delta G0 from 2 moles NO2 to 1 mole N2O4. Here's delta G0 from 1 mole N2O4 to 2 moles of NO2. If I start with either of these, is that what happens? Hell no. I get the delta G change, not the delta G0 change, and I go to equilibrium. That's the same thing that happens here. It's the same thing. The calcium carbonate dissolves in the water spontaneously, because all you did was put it in the water, until the equilibrium condition is established. End of story. Now then, from a delta G0 standpoint, since we're aiming to look at this reaction, where delta G0 has been related quantitatively to the equilibrium constant for a reaction. Here, K is the equilibrium constant, not temperature in Kelvin. We made the statement that very few reactions are at equilibrium in the standard state. Very few. But I have 2 examples. They're really not reactions, they're physical changes. But still they can be looked at from a thermodynamic standpoint. You've studied now the phase diagram for water from an appropriate perspective, from a G perspective, because that's what a phase diagram is. And you recognized, if you looked at the diagram carefully, or if you want to look at it now, that at an external pressure of 1 atmosphere and 0 centigrade, these materials are in equilibrium, aren't they? And by definition, they're in the standard state. Well then, that means the standard free energy of formation of water solid equals the standard free energy of formation of water liquid at these conditions. Which means, since equilibrium exists, delta G0 is 0 for this transformation at these conditions. What about this transformation at these conditions? External pressure is 1 atmosphere, which is equal to the partial pressure of water vapor, which is equal to the vapor pressure of water liquid at these conditions. Equilibrium exists at these conditions, 100 centigrade. So notice, for this equilibrium system, at 100 degrees centigrade, pH2O gas is 1 atmosphere. Delta G0 is minus 2.3 RT log K. And from a thermodynamic standpoint, how do I write the equilibrium constant for this reaction? From a thermodynamic standpoint, or shall we say from a preferred thermodynamic standpoint, how do I write the equilibrium constant for this reaction? What is it? You tell me and I'll write it right now. What shall I write? That's it. Partial pressure water vapor. Pure liquid, pure solid. We don't have those in equilibrium constants. The concentrations don't change as equilibrium is established. Well then, if at these conditions the partial pressure of water vapor is 1 atmosphere, which it is, what's the log of 1? How about that? So delta G0 is 0, isn't it? And so, we'll now, just to give you a better understanding of where these relationships come from and what they mean, have you look at this hypothetical reaction and considerations which follow with this hypothetical reaction, leading to something we already learned about way back in chapter 17. Q the reaction quotient. So we'll pick it up from this point next time.